Okay, 12.5. Again, we're going to start with an example. So this is example number 8, continuing from yesterday. Consider the following two planes. First plane is x add y add z equals 1. The second one is x subtract 2y add 3z equals 1. We are going to calculate or find two pieces of information. First, we are going to find the angle between the two planes. And the second thing that we are going to do is we are going to find symmetric equations for the line of intersection of the two planes. So we can tell right away our planes are not parallel. That means that they have to intersect. The only way that two planes are going to intersect is in a line. Okay, what two pieces of information do we need to write the equation of a plane? From yesterday. Point and, yeah, the perpendicular vector. So for part A, we need to find those two perpendicular vectors. So the perpendicular vector for the first plane is 1, 1, 1. Perpendicular vector for the second plane is 1, negative 2, 3. How am I going to find the angle between these two? Cosine of theta equals, yep, n1 dot n2 over the magnitude of n1 and then the magnitude of n2. Okay, so if we do the dot product, we get 1 times 1 is 1, 1 times negative 2 is negative 2, 1 times 3 is 3. Magnitude of the first vector is the square root of 3. The magnitude of the second vector, we get 9 add 4, which is 13. 13 add 1 is 14. So this is 2 over the square root of 42. Theta then ends up being about 72 degrees. Okay, so now my question to you, is this the angle between the two planes? Because the vectors we have are not on the plane, they're perpendicular to the plane. So is this actually the angle that we're looking for? Are you sure? That angle is acute. Okay, so let's try to picture something. So if we look over here, we have these two planes, right? This is the first perpendicular vector. This is the second one. This is the angle that we just found. Is that the angle that we want? Or is it equal to the angle that we want? Yeah, it is. Yeah, this is a parallelogram. So it's not directly the angle we want, but it's the same as the angle that we want. Does that make sense? I know that's kind of hard to see. So that is, in fact, the angle that we wanted. So that's just something to be cognizant of. Okay, so then for part B, we need to write symmetric equations for the line. So there's two pieces of information we need. We need a point, and we need a parallel vector. So first, we need a point on line L. Whole bunch of options for this point. We're going to find the point where our line intersects the xy plane. So one point is the point where our line intersects the xy plane. We did an example like this yesterday. XY plane means that z is going to be 0. So when z is 0, that first equation, x plus y plus z equals 1, that becomes x plus y equals 1. Likewise, in the second plane, if we set z to be 0, we get x minus 2y equals 1. Okay, I'm going to subtract the two equations. So x minus x will give me 0. Y minus negative 2y will give me positive 3y. 1 minus 1 will give me 0. So we get y to be 0 as well. Using either one of those equations, you get x to be 0. Sorry, 1. So our point then that we're going to use is the point 1, 0, 0. Again, that's just one such point. Okay, next thing we need is that parallel vector. So if that line L lies on both planes, it must be perpendicular to both normal vectors. So the n1 and n2. Does that make sense? If the line lies in the first plane, it's going to be perpendicular to the first normal vector. If it lies in the second plane, it'll be perpendicular to the second normal vector. Okay, so how do we find a vector that is perpendicular to two other vectors? So I have vectors n1 and n2 up here. You take the cross product. Yeah. So the vector that we're going to use is going to be the cross product of n1 and n2. We've done multiple cross products at this point. Do we want to still do the cross product again?
No.
Great. I'll tell you, it ends up being 5, negative 2, negative 3. So finally, we have a point. We have our normal vector. So now we need to write the equation of the line. Remember that you were asked to write symmetric equations. So we're going to have x minus 1 over 5 equals y minus 0 over negative 2, which equals z minus 0 over negative 3. So that is the symmetric equations for the line of intersection of those two planes. Questions on writing equations of planes or lines before we get on to the last type of problem that you're going to do this section? No? Okay. Last thing that we are going to talk about in this section is distance. Distance problems. I'm going to give you a formula for this. There's 3 different types of problems that I could ask you using the same formula. First type of problem that you will be asked is to find the distance between a point and a plane. I could ask you to find the distance between parallel planes. And I could ask you to find the distance between skew lines. All 3 of those questions are going to be answered using the same theorem. So here's the theorem. The distance between a point we're going to call that point P of x1, y1, z1. And a plane, ax plus by plus cz plus d equals 0, is given by the following equation. D equals, the numerator is going to be the absolute value of a times x1 plus b times y1 plus c times z1 plus d. So those vertical bars in this case mean absolute value, over the square root of a squared plus b squared plus c squared. So what this is saying is if I give you a point and I give you a plane, this a times x1, you're going to take that a, multiply by that x1. B times that y1. C times that z1, and add d. Take the absolute value and divide by the square root of those three. Does that formula make sense? Okay, I'm skipping then the first type of problem, distance between a point and a plane, because it's just plugging right into the formula. Is that okay? One thing I want to point out about this formula, though, is that your plane has to be in this form. Has to be equal to 0. Cannot be equal to d. So if you set it equal to d, you're going to get the wrong answer. So make sure always equal to 0. So we have 2 examples with this, and then we are done with notes for today. Okay, next example. We are going to find the distance between the parallel planes that are given by, the first one is x plus 2y minus 2z equals 3. And the second one is 2x plus 4y minus 4z equals 7. Before we find the distance, the first thing I want to know is, how do we know that these planes are parallel? Yeah, their normal vectors are scalar multiples of each other. So the first normal vector is 1, 2, negative 2. Second normal vector is 2, 4, negative 4. Scalar multiples of each other, that tells us that the planes are parallel. So in order to use the formula, we need a point and we need a plane. We have 2 planes, so really what we need is we need a point on one of the planes. So you're going to use one plane, like maybe we'll use this as our plane, and then we need a point on this plane. So then we would find the distance between the point on this plane and that plane. Does that make sense? Okay, so first thing we need is we need a point on one of the planes. Suggestions for how to find a point on that first plane. Any point at all.
X-intercept?
Yeah, find the x-intercept. Let y and z be 0. So for that first plane, we're going to let y equal 0 and z equal 0. When we do that, we get x equals 3. So the point that we're going to use then is 3, 0, 0. So now we need to find the distance between that point and that plane. We are not yet ready to use the formula. Why not? Right. Remember how I said that your plane has to be set equal to 0? Please make sure you do that before you use the formula. So this is going to be 2x plus 4y, subtract 4z, subtract 7 equals 0. Okay, now we're ready to find the distance. In the numerator, we have a times x1, so 2 times 3, plus b times y1, plus c times z1, plus d, which is that negative 7. Denominator is the norm of the normal vector, so that 2, 4, 4. Okay, so we get 6 minus 7, so negative 1, but you're taking the absolute value, so that ends up being positive 1. 16 and 16 is 32, add 4 is 36, the square root of 36 is 6. So the distance between those parallel planes is 1/6. Okay. Questions on the formula before we do the last example, which is going to involve skewed lines? No? We can keep going? Okay. Just so you all know, on a test, I will not give you any formulas. So that formula that I just showed you, you guys are going to have memorized. Last example. In example number 5, we showed that L1 and L2, which are below, are skew. Find the distance between them. L1, I'm giving these parametrically, was x equals 1 plus 4t, y equals 5 minus 4t, and z equals negative 1 plus 5t. The second line was x equals 2 plus 8t, y equals 4 minus 3t, and z equals 5 plus t. Okay, so at this point, we really don't have anything that we need for the formula. We need a point and we need a plane. So what we're going to do is we're going to consider these two lines, since they're skew, as being on parallel planes. So then we're going to use one of the lines on one plane that we're thinking of to find a point, and then the other skew line we're going to make a plane through. Does that make sense? Okay. So first we're going to start with the plane. We need a point and a normal vector to write the equation of the plane. Like we said, we're going to consider those two lines to be on parallel planes. Okay. So what we're going to do is we're going to use line 1 to find a point. We're going to use line 2 to write the equation of the plane. So we need a point on line 1. How can I find any point on line 1? Thank you. Any point on line 1? Yeah, plug in a value of t, like maybe t equals 0. Thank you. Okay, so we need some point on line 1. So we're going to plug in t equals 0. When you do that, we get 1, 5, negative 1. That is the point that we are going to use. So now, we're going to need to write that plane for L2. Do you guys see where I'm headed here? Okay, so again, to write the plane, like we said up above, we need a point and we need a normal vector. We're going to find a point the same way. So plug in t equals 0. That's going to give us the point 2, 4, 5. How do we find a normal vector for line 2? So how do we find a vector that is perpendicular to the vector for the direction of line 2? Because that's what we need in order to write the plane, the equation of the plane. What is the only way so far that we've talked about finding a vector that is perpendicular to something? Cross product. Would that help us here? Cross product requires two vectors. Do we have two vectors at all in the problem? L1 and L2, we have those two vectors. What happens if I cross them? I'll get a vector that's perpendicular to both. Is that helpful in writing the equation of the plane? Yeah. I don't really care that the vector is perpendicular to L1, but I care that it's perpendicular to L2. Does that make sense? Okay, so we're going to cross the two. So we're going to cross the vectors for L1 and L2. That's really better notation, not that one. Again, are you okay if I just tell you what it ends up being? Okay, great. It's 11, negative 36, and 20. So that vector is perpendicular to both lines, Therefore, it's going to be perpendicular to the plane for L2. So the equation of our plane then, we're going to be using that vector, that point. So we get 11 times the quantity x minus 2 minus 36 times the quantity y minus 4. Add 20 times the quantity z minus 5. All that equal to 0. You end up getting, when you multiply all of that out, 11x minus 36y, add 20z, add 22 equals 0. So now, this is the point that's on L1. This is the plane that L2 falls on. So now we are finding the distance between this point and this plane. Using that same formula, so we have 11 times 1 plus negative 36 times 5 plus 20 times negative 1 plus 22, the absolute value of all of that, all over the square root of 11 squared, add 36 squared, add 20 squared. If you trust my calculations, this ends up being 167 divided by the square root of 1,817, which is approximately 3.918. Okay, that's distance for you. Does this make sense? The ideology behind this? Or the reasoning?
Can you explain quickly one more time, like why we need a point and a plane from each line? And so it's just like that's just the equation.
So let's say that we have our two lines here.
Yeah.
We're going to consider this to be on a plane and this to be on a plane.
Mm-hmm.
So if I choose a point on this line, I'm then finding the distance between this point
Yeah.
and the plane that I made this be on.
Okay.
Does that make sense?
Yeah.
Were the vectors you crossed, like the constants in front of t? Like
Were they what?
negative 4, 5? Like, or do you get the...
Yes.
Okay.
Yeah, the 4, negative 4, 5, and the 8, negative 3, 1. That's what I crossed to get this one. Anything else?
On the test, because we don't have a calculator, do we just leave everything in like,
I would expect you to leave it like this.
okay.
And if I recall, I did not give you an example with numbers crazy like this. It's going to be more like the last example that it ended up being just 1/6.